Hello everyone. In this video we're going to be evaluating a very interesting, very complex expression. We have I to the power I, and I is defined as the number whose square equals -1. So I is the imaginary unit. We're going to talk about some interesting formulas, the polar form of a complex number, Euler's formula, and then I'm also going to be showing you a graph. Alright, let's get started. So first of all, we can use I to write complex numbers. So x plus yi, if x and y are real numbers, z equals x plus yi is defined as a complex number. Obviously, real numbers are also complex because if y is equal to 0, you get x, which is real. So they're kind of subset of complex numbers. Anyways, so one of the biggest questions is that, is this going to be a complex number as well? Because I is complex, a complex number to the power complex number, is that going to be complex or real? All right, let's go ahead and find out. First of all, let's talk about Euler's formula. So Euler, obviously, when you look up Euler's formula, a couple of different things are going to come up, but one of which is very important. E to the power ix equals cosine x plus I times sine x. Now, x is measured in radians. That basically describes the angle from the positive angle. You know, we're going to talk about it on the unit circle or in the coordinate system. So e to the power ix is an exponential, but I is imaginary, x is real, it's an angle measured in radians, so on and so forth. So this allows us to write a complex number that's written in polar form. We can turn it into an exponential form. And where does this come from? Obviously, maybe I shouldn't use x plus yi because that's kind of misleading. How about we use a plus bi? So here you can kind of see the association between these two things. One of the things that we're going to define is going to be how to express a complex number in polar form. So here's what we do. We're going to define the theta as the angle measured in radians is a positive angle. It's counterclockwise, and a and b are the coordinates. So basically, a complex number can be expressed as a point on the coordinate plane or a vector. But how do you turn this into a polar form? You can do that by using the following fact. R as defined as the modulus, which is the square root of a squared plus b squared. So if you take out a r, then you get a over r plus b over ri. A over r becomes the cosine of an angle, and this becomes the sine of an angle, so on and so forth. And you can define the tangent as well. But let's go ahead and do this for I. Now, I is kind of easy because we can write it as 0 plus 1 times I, and its modulus is 1 because 0, 1. The length is going to be 1, right? So here's how we express it here on the coordinate system. And from here, you can actually easily find the argument or the angle measured in radians. In this case, it is going to be pi over 2. So this is our imaginary number. This is the imaginary axis. This is the real axis. So if you have any complex number whose imaginary part is 0, then it's going to be on the real number line. Okay, so this is I expressed in polar form. How do we raise it to the power I? But we have to turn it into an exponential form. So let's go ahead and do that. So I can be written as, since the angle is pi over 2, we can write it as cosine of pi over 2 plus I times sine pi over 2. Now, in this case, I kind of ignored the r because r is 1, so we don't have to worry about it. So we're good. Now we're going to raise this to the power I. But using Euler's formula, we can write this as e to the power I times pi over 2. That's beautiful. Now, we're going to go ahead and raise I to the power I, which means e to the power I pi over 2 to the power I. Now, the exponentiation rules or exponents, whatever, tells us that we're supposed to multiply these two things. So it's going to become e to the power I squared pi over 2, but we know by definition that I squared is equal to -1, so this is going to be e to the power negative pi over 2. Great, so that's the answer, and as you know, this is a real number, and you're like, are you for reals? Yes, this is a real number. Interesting, right? And we're going to look at the value of this when I show you the graph, because we're going to talk about some solutions, right? So real and complex solutions. But we could also do the following. I cannot be written in a single way. You could also write, since pi over 2 can also be expressed as pi over 2 plus an even multiple of pi, which is, or integer multiple of 2 pi. So we can also write I this way, if you think about it. We can basically add multiples of 2 pi to it because it's not going to matter. It's just going to give us more rotations. And this can be written as e to the power I times pi over 2 plus 2 pi n. And then when you raise, this is I, by the way, when you raise it to the power I, it's just going to become e to the power I squared times this. And then you're just going to replace I squared with -1, and this is going to give you e to the power negative pi over 2 minus 2 pi n, but negative n is just another integer, so we can call that k, and this can be written as e to the power negative pi over 2 plus 2 pi k. So this is just another way to write it in more general form, I to the power I, and if you replace k with 0, you get the first solution. If you replace k with 1, so on and so forth. Obviously, there are infinitely many solutions as long as k is an integer. Okay, great. Now here's one thing that I want to talk about, but first I want to give you a little bit of something. So we're basically looking at the following, right? We have y equals x to the power x, and we found that I to the power I is equal to e to the power negative pi over 2. So let's just go ahead and stick with this one for now, okay? So this indicates that, hey, if this is equal to e to the power negative pi over 2, we're supposed to get x equals I from here, right? Because I satisfied this equation. At least that's one of the solutions. So I to the power I is equal to this number right here, and that's a real number. But I is not a real number. So what is the issue here? The issue is the derivative, the maxima and minima, and so on and so forth. So let's go ahead and ln both sides of this function. This becomes ln x to the x, and then ln y becomes x ln x, and I'm going to go ahead and differentiate by using chain rule. Y prime over y is derivative of x times ln x plus the derivative of ln x times x. This becomes 1, and y prime becomes y times this, which is x to the x times ln x plus 1. When you set it equal to 0, you get ln x equals -1, which means x equals 1 over e. And then if you plug in 1 over e, you get 1 over e, comma, 1 over e to the power 1 over e, which is e to the power -1 over e. So that point is actually a minimum point on the graph, because if you remember the graph of y equals x to the power x, it kind of looks like this. And it makes a minimum at this point. But what happens when you have a horizontal line? That's what we're going to look at right now. Let's go ahead and take a look. And here's our graph, y equals x to the power x. And the solution for I to the power I. So this is equal to I to the I. So we're expecting to get an x equals I here, but there is no intersection point because I is not a real number. And obviously this value here is less than the minimum y value that you see here. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe, take care, and bye-bye.